All right, guys, so let's bring it together with some right triangle trig. So in geometry, you definitely learned about trigonometry. You learned that each right triangle has these three sides. One of them is the hypotenuse. It's across from the 90-degree angle. And then the other two sides are labeled according to which angle you use as your reference. So like if I use this angle, this leg is the adjacent side and this leg is the opposite. If I were to move that angle over here, then they flip. So if you use the lengths of the sides of the triangle, you can actually make 9 ratios, but 3 of those are pretty trivial, so we don't really use those. So that means we have 6 left that we are going to define and use to problem solve. And we're just going to start with right triangles only, but then eventually we're going to move to oblique triangles, which are triangles that don't have to be right triangles. Okay, and so the trig functions and their values that you used for angles and triangles can be defined for angles of any size. So we can do eventually angles that are even bigger than 90, which aren't technically triangles like you're used to, but we can create triangles using angles that are bigger than 90. So first, let's go back and remember what we can about trig. So first of all, let's see what you remember, and I've got it written below, so I'll scroll down in a second, but do you remember what ratio sine was? How about cosine? What side to what side? And how about tangent? Maybe you remember the shorthand version, SOHCAHTOA, right? If you remember that, it's probably pretty easy. Sine of an angle is the opposite side over hypotenuse. Cosine of an angle is an adjacent side over hypotenuse, and tangent of an angle is opposite over adjacent. Okay, so again, we're going to use these with our unit circle and a rotating point. But remember, I said we were going to use 6 trig ratios. So we only have these 3 that you might have learned last year. Maybe you touched base on some of these last ones, but these are the others. So we have cosecant, secant, and cotangent. Okay, so you might be noticing these words right? Like tangent and cotangent. And then secant and cosecant, these two actually are co-functions, and so are sine and cosine. So there's relationships this way, but then the cos will also have relationships, but we'll talk about those later. So I hope that everybody sees these are just the reciprocals. So like sine's reciprocal, if instead of opposite over hypotenuse, I did hypotenuse over opposite, that's cosecant. So you're going to want to start thinking of sine and cosecant as being reciprocal functions to each other. And same thing for cos and secant, and same thing for tan and cotan. So again, you're really going to want to connect those, like cosine and secant are reciprocal functions. But that's pretty much it for that. Okay, so let's see if we can connect the coordinates that we were getting in the previous video with the wrapping function to this cosine and sine. Remember, yesterday we talked about it. Okay, so let's look at a point out in space. And we'll put that point on the unit circle, which means the hypotenuse is 1, right? Okay, so let's talk about how we're going to get the x side and the y side, right? Because that's what we want. We want this coordinate, that point. Okay, so if we wrap a particular angle, so we have to know that angle. If we go a particular angle, let's see if we can figure out how to get x and y using trig. Okay, well, if we know theta, let's just get x. So if we want to solve for x, we would use x and the side we know, which is the hypotenuse, and the theta. So what are those two sides? Where are they located in terms of this angle theta? Well, one is the hypotenuse and x is the adjacent side. So which one uses adjacent and hypotenuse? Cosine. So I could write cosine of my angle would be equal to the adjacent side over the hypotenuse, which, what? That means that cosine of theta is just x. What? That's great. Let's look at the y value. Well, if I want to use y, I'm going to use y and the hypotenuse, which is opposite and hypotenuse. Guess who uses opposite and hypotenuse? Sine. So sine of the angle would be the opposite, y, over the hypotenuse, 1. So check it out. We get sine of theta is the y value. So we said this yesterday, or in the previous video. We said if you wrap a particular angle on the unit circle, then that point is going to be, the x value is going to be the cos of the angle, and the sine is going to be the y value. That's awesome. This is how we can also wrap bigger. We can do angles that are bigger than 90, right? So this is what I mean. Like if I had an angle here, like let's do a radian value. Let's do 4 pi over 3. So if I wrap to 4 pi over 3, 4 pi over 3 would give me, that would mean I go 1 pi over 3 past pi. So I make my little reference angle. Pi over 3 is what reference angle again? 60. And when we do reference angle, we put a little theta with a hat on top. I'll draw that one more time so you can see what I did. So it's like a theta with a hat. That's a reference angle. So this is a 60-degree reference angle, or a pi over 3 reference angle, but 4 pi over 3 is what got me all the way here. Okay, so now we know the hypotenuse is 1, and we know that the adjacent side here, the short side, is 1/2 negative, and this side is negative root 3 over 2. So what does that mean? That means that the cos of 4 pi over 3 is x, negative 1/2. And the sine at 4 pi over 3 is the y value of that, negative root 3 over 2. That's pretty cool. That means you can get those values really quick by just thinking of your triangle. Okay. But that means, of course, that there are times, since I am setting up ratios, there are going to be times when I have a fraction that causes a problem. So we need to define these 6 trig functions. So we can say, this is if I'm on the unit circle. Eventually we'll talk about circles of different size, and it's pretty much the same with a slight difference. So, okay, we know that cos of theta is adjacent over hypotenuse, but it's also now x if I'm on the unit circle, the x coordinate. Sine is opposite over hypotenuse, or the y value on my unit circle. Tangent, if you think about it, your little point on your circle. Tangent, if you remember, is opposite over adjacent, right? And so if I do opposite side over adjacent, I'm going to have y over x. So that's how I get tangent is y over x. And then my reciprocals would just mean I flip all these. Now remember, when you reciprocate a whole number like x, it becomes secant 1 over x. Remember the reciprocal functions. So why do you guys think these reciprocal functions and tangent, because tangent also is a fraction, what would make these fractions have an issue? What about fractions can cause an issue? Yeah, denominators can't be 0. So we have to do a little bit of restricting. So you're going to see me write some restrictions. So this means that x can't be 0 for tangent. And so we need to think about what values of theta would give me a 0 for x. So let's think about our little unit circle. So I'll draw my little unit circle again. So what angles would give me a 0 for the x coordinate? Well, remember, here's your x-axis. So like if I'm out here, this is at 1, 0. So that is not x being 0. This little guy is, oh yeah, that one definitely has an x being 0. And then this guy has an x being 0. So that means pi over 2 and 3 pi over 2 would cause a problem. Do you guys see that? Pi over 2 here, 3 pi over 2 here. Those would both be a problem. And then any wrap of that. So normally when we do multiple wraps, we go all the way around the circle. But this one, you're going to keep having issues here and here, and those keep repeating every half circle. So instead of having to say like pi over 2 and every wrap 2 pi k, you can say I'm going to have to get rid of pi over 2 because that would be a problem, and then every half circle would create another problem. So I'm going to do it like this. So theta cannot be pi over 2. You can't have a pi over 2 angle. And then I want to get rid of anything that's half a circle away. How much is half a circle? Pi. So instead of 2 pi, I'm going to do pi k. And then I'm going to say, remember, k is an integer. Okay, so that would get rid of all angles that have an x value of 0. All right, let's do cotan. Cotangent has a y on the bottom, which means y cannot be 0. And let's see where y is 0. Y is 0 here and here, which are 0 and pi, right? So I could say, okay, well, theta can't be, the first thing it can't be is 0. And then once again, I want to get rid of every half circle move from there. So then every pi k. And we can talk about this in class if you guys need to clear this up a little bit more. I don't really need this 0 here because it doesn't do anything. So I could just say pi k. Okay. And then these last two are easy because now you already know. Secant is the reciprocal of cos. Sorry, it's up here on the top. Secant is the reciprocal of cosine. So that means x can't be 0 because the x would be on the bottom. And we already know. We know that that's going to get rid of pi over 2. Notice I'm saying cannot be. Theta can't be pi over 2 or any half wrap of that. Half wrap because I'm not going a full circle. Same thing for cosecant. The y is now on the bottom because cosecant is the reciprocal of sine, so y can't be 0, and that corresponds to theta not being able to be pi k. Again, we can look more at that in class. Okay. All right. After that, it's pretty much us just practicing finding these values on the unit circle, which we'll do in class together. So I'll see you in class.